Welcome, everyone. Thank you for joining us today on behalf of ESCSI member companies and David Fuqua from Tensar. We appreciate your taking the time to participate in our webinar today. It means a lot to us that you've chose to spend the next 50 minutes to an hour with us, and we hope that at the end of this time that you end up with a nugget that you can take away and perhaps be useful for some of your clients. I'm Jack Moore. I'm one of Arcosa's marketing and technical managers, and with Arcosa Lightweight. And again, with me today, co-presenting with me today is David Fuqua from Tensar, and he and I will be co-presenting on geotechnical applications for ESCS lightweight aggregates. Before we begin, a little housekeeping, a few housekeeping items which are very familiar to many of you that participate in webinars. Please mute your audio and turn off your cameras if you don't mind. And any questions that you think of during the presentation, if you could type those in the chat box, and we'll try to address those at the end of the presentation. So with that, let's get started. Sorry. The presentation outline consists of the following. We'll talk a little bit about ESCSI and what it is, and the organization and what it is. We'll discuss lightweight aggregates in particular, their history, markets in which ESCSI members participate. We'll talk about the manufacturing process and show you a map with some plant locations. After that, we'll segue into an overview, a very general overview of ground improvement, the methods that are available in the market today, lightweight fill options that are available as tools to solve your challenging site conditions, and we'll talk about the relevant physical properties of each. After that, I'll segue to David's portion, and he will give us an overview of the MSC market from Tensar's perspective. He'll talk about Msc Structures, the types, spacing options, and specifically, how a lightweight fill or a lightweight aggregate can impact an MSC design if it's needed for bearing capacity or settlement concerns. So hopefully that sounds good to everybody. And so a little bit about ESCSI. It's the acronym for the Expanded Shale, Clay, and Slate Institute. It was founded in 1952 as the trade association for manufacturers of rotary kiln produced expanded shale, clay, and slate lightweight aggregates. Its primary mission is to sponsor research and develop marketing and technical collateral that's used by engineers, contractors, and owners on the benefits of lightweight aggregate solutions. Many of our members are active in key organizations such as ACI and ASTM, with many of our members participating on relevant committees within those organizations. This map depicts the locations of manufacturing facilities of the ESCSI members. Over the last decade or so, there's been some consolidation in the industry, and the member companies that you see located on this map are owned and operated by the 5 companies you see here. Not shown on this map are terminal and distribution point locations. So in all likelihood, there's a source of lightweight aggregate within a reasonable distance of many projects in the U.S. So ESCS material, or expanded shale, clay, and slate, I'll interchange those nomenclatures in the presentation. It's an invention of Stephen Hay Its roots are in the brick industry. A little over 100 years ago, Stephen Hayde was making brick in a beehive kiln like you see here. And occasionally, when he took the brick out of the ovens, he would get something that looked like this. So a bloated brick is not something you want if you're in the brick business. So those were coals that he crushed and sold to local concrete producers. And ultimately, they found that the finished product that was made with the crushed cold bloated brick weighed less. So Stephen Hayde made some hay out of this, and he decided to intentionally make bloated brick, quote unquote, and he created a method to do so. He studied time-temperature relationships and discovered that keeping the material stationary, like in a beehive kiln, wasn't important. He determined using a rotary kiln was the best way to make consistent product. Over the years, there have been significant improvements to the process with automated controls that now produce product with greater consistency, and not the least of which is very much improved operator safety. Stephen Hayde received his patent in 1918, which was in the middle of World War I. At that time, he gave the U.S. government the rights to the patent so they could develop lightweight concrete for ships due to the shortage of steel at the time. So in World War I, several concrete ships were produced, and the picture on the lower right is the USS Selma, which was the very first one that was produced. It was commissioned in 1919. In World War II, the same thing happened. There was another steel shortage, and consequently, more concrete ships were produced. After the wars, lightweight concrete started to be commonly used for other things, such as high-rise buildings, bridges, bridge decks, and later in precast, pre-stressed elements, such as the lightweight double T you see here on the lower right, reducing the weight of the elements to get more economy from shipping more product on a truck, which produces a freight savings. Over the years, other markets developed. Concrete masonry began in the 50s, and today is still the single, largest market for lightweight aggregate in the country. In the 60s, it was used in asphalt applications and hot mix asphalt at that time, but today the primary asphalt use is for pavement preservation through chip seal applications. And in the 70s, it began to be used for geotechnical fill applications, and obviously that application is the focus of this presentation today. The photo on the left provides a good visual of the volume difference in ESCS lightweight aggregate compared to 4H select fills and aggregates. Each of the vials contains roughly a pound of material. And the center container is a compilation of material from all the ESCS manufacturers. And as you can see, it has twice the volume compared to the other materials. So wrapping up this summary of ESCS traditional markets, a significant portion of the annual production goes into concrete and concrete masonry applications, and where we routinely support the production of lightweight concrete mixes with very high compressive strengths. So focusing now on the manufacturing process of expanded shale, clay, and slate lightweight aggregate, it's pretty straightforward. The raw materials, select raw materials are excavated and harvested, and they're typically brought to some sort of a storage area that's usually covered to keep the material as much out of the elements as possible, especially in the wintertime. At that point, it's fed into a series of conveyors that bring the raw material up to the entrance to the rotary kilns. And this photo shows a shot of a typical 4-kiln operation. Inside the kiln, obviously, is where all the magic happens. The material is heated to around 2,000 degrees Fahrenheit. At this point, the material bloats or expands, and the particles end up with a lot of air voids inside, and that's consequently what makes the product lightweight. At the end of the process, you end up with a ceramic material that's very strong, durable, and environmentally inert, and has a low density as well. This is a chart that summarizes the ground improvement or modification methods and technologies that's available on the market today. A lot of these are going to be very familiar with many of the folks in the audience, but I wanted to compile these to show that where lightweight fill fits in the ground improvement modification options. Using lightweight fills, you can reduce the demand of reinforcing materials in structures, and perhaps either reduce or, in some cases, maybe eliminate more costly ground improvement methods. And we'll talk specifically about in general, about the lightweight fills that are listed in the bottom right. All these products and methods and technologies are summarized in Federal Highways Ground Modification Method reference manual. It's a free download, so if you don't have this, it's an excellent reference, and I suggest you get it. Within that reference is this chart, and I thought it would be applicable to discuss steps 6, 7, and 8 in the ground modification technology selection process. And as in any project consideration, the site constraints must be taken into account, and certainly not the least significant option there is considering project risks. And obviously preparing a preliminary design is the function of the geotechnical engineer. But considering project risk, using lightweight fills can minimize the impact or possibly eliminate more riskier ground improvement modifications. So lightweight fills can bring a lot to the table with those kind of strategies. Some of the methods, just in summary, some of the methods that are available include consolidation. This usually takes the form of prefabricated vertical drains and an accompanying surcharge load. Chemical stabilization is another option, and that commonly involves soil mixing. Aggregate columns or some sort of an intermediate foundation system, such as a round aggregate pier or a stone column. Densification, which is typically vibro compaction and deep dynamic compaction. And load reduction, which is where lightweight fill materials fit. The reinforced soil structures is another method, ground improvement method, and these typically take the form of mechanically stabilized earth slopes and walls. And David's portion of the presentation will take a deeper dive into these applications. So using one or more of these methods, you can increase bearing capacity, attempt to control vertical and lateral deformations, you reduce imposed loads, and increase lateral stability. This chart summarizes most of the lightweight fill materials that are available on the market today, and generally their range of unit weights. As you can see here, I put ESCS materials at the top of the list, and they tend to be the heaviest of the lightweight fill materials on the market today. But they offer some construction considerations that I'll discuss a little bit later. But among the players that are more common, low density cellular concrete, expanded polystyrene, foam glass aggregate, which is a relatively new player in the market today. And you can see the unit weight ranges for each one of those. Taking a brief look individually at a few of the lightweight fill options on the market today. Expanded polystyrene is one option. It's a plant manufactured material, usually in 6x3 by 1.5 foot block, with unit weights that range from 3/4 to around 2 pounds per cubic foot. Some construction considerations for this option include you have to avoid continuous vertical joints, so the block need to be laid in a running bond, similar to the way you do a brick veneer. You use a mechanical connection between the blocks for shear transfer, so that has to be installed. And you should cover the EPS with a suitable hydrocarbon resistant membrane or some sort of impervious cover to limit damage in the event of a hydrocarbon exposure. And you should cover it as soon as practical to prevent displacement by wind or water. Another thing to consider is EPS is manufactured in North America with a flame retardant, but it's still somewhat combustible. So open flame procedures such as welding should be carefully monitored in and around an EPS embankment. As I mentioned earlier, foam glass aggregate is a relatively new player in the lightweight fill market. Although it's not a new player in the national market, it was developed in Germany in the 80s and started being used in Norway in the 90s as a thermal barrier in roadways. It has a dry bulk density of around 12 to 15 PCF, with estimated compacted dry densities in the 14 to 19 PCF range, and particle specific gravities are less than 1, so the material is buoyant, and it's also commonly uniformly graded. So for MSC applications, foam glass probably should be encapsulated or covered with a non-woven geotextile to limit any potential migration of fines. Another option, lightweight fill option, is low density cellular concrete, or commonly abbreviated as Ldcc. It's a job site produced material that's a watered cement slurry with a foaming agent. There's no sand or gravel in the mix. So the water cement slurry, after the addition of the foam, the cementitious material encapsulates the foam air bubbles, and when the foam dissipates, it leaves a cellular concrete core structure when it's cured. The material is pumped into place, which can have some advantages, especially in high density urban locations. Common ranges for MSc structures or for unit weights are roughly 30 to 42 PCF. As you would imagine, low density cellular concrete is fairly cement intensive. So for a 30 PSF cast density, there's a little over 500 pounds of Portland cement per yard of Ldcc. Some construction considerations using this option are probably pretty obvious. Bulkheads need to be used to limit flow distance from the discharge point to minimize segregation. Segregation can create some weak zones within the reinforced fill, which should be avoided. A staging area is required for batching, mixing, and placing. The solution is fluid and almost always requires some sort of formwork. The lift thicknesses need to be such that workers can shape the surface while waiting in the mix, and you should obviously allow drying time between lifts. So this brings us to ESCS lightweight aggregates. Their bulk density is less than half that of porate aggregates, typically in the 35 to 60 PCF range, depending on the grading and the manufacturer. That results in compacted densities of around 40 to 65 PCF. Its specific gravity is greater than 1, and it has excellent internal friction properties. It almost always tests greater than 40 degrees in direct shear. As I mentioned earlier, ESCS material is probably one of the, if you want to refer to it this way, one of the heavier lightweight fill materials available on the market today, but it has considerable construction advantages. It can be trucked to job sites in tandem or trailer dump vehicles. Grading contractors can use their conventional earthwork equipment to handle and place the material. Generally, very little compactive effort is required to achieve a suitable density. And probably the best thing about it is there's no specialty contractor that's necessary. To give you an idea of some of the pertinent physical properties, this is a sample where we had an ASTM D98 test done, which we commonly call a one-point proctor. But this particular sample had a compacted dry density of just over 50 PCF. This is a sample that was put through a direct shear test, and you can see this one had a phi angle of 50 degrees. So, and in Dave's presentation, he will discuss the impacts of reducing unit weights and internal friction angles to the design of an Msc structure. The material is very durable. LA abrasion results for this particular sample was 34% loss. It's common to see AASHTO specification requirements of no more than 40% loss. So this material, ESCS material, would fit in that category very nicely. So the combination of high internal friction angle and low unit weights, considerably reduces the pressures on lateral earth pressures on walls. Running through a calculation of lateral earth pressure, it's a function of the material density, the wall height, and a K value, which is a function of the internal friction angle. So running through the math on comparing a select fill at 150 PCF with a phi angle of 30 degrees and a lightweight aggregate with a density of 55 PCF and a friction angle of 40 degrees, you get 1/3 of the lateral earth pressure compared to a quarried select fill. So that can be significant in when the design of components are taken into account. Same is true for applied vertical stress. You reduce the weight, reduce the applied vertical stress. In this example, comparing a 55 PCF lightweight aggregate fill to a normal fill, you end up with less than half of applied vertical pressure, which can be significant if there's a bearing capacity issue. So I want to segue now to David's portion of the presentation. David's had multiple roles with Tensar, and he's currently the area engineer, one of their area engineers, and primarily covers the southern U.S. He has significant experience in Tensar's grade separation market. And prior to joining Tensar, Dave wore a couple of hats. He was president of Specialty Civil Designs that focused on MSE designs and ground improvement. And he was also president of Terraform, which was a construction company that focused on foundation improvement and retained earth structures. So, David, it's all yours. So, Abigail, if you could switch us, that'd be great.
Excellent. Well, we appreciate everybody tuning in, and we hope that you take something away from this. What I'm going to focus on is the use of alternate backfills, geotechnical properties for Msc structures. Just to expand a little bit on what Jack had mentioned about myself, I am the area engineer for Tensar in the South US. I've had over 13 years with Tensar that spread over 2 tours of duty, once back in the early 90s, and I've been back with them now for about 8.5 years. 17 years in the design build business, and you can tell by all the gray hair I have that it's kind of a trying business. I've been a PE for over 38 years and currently licensed in 13 states, mainly in the Southeast. What I would like to talk about today would be types of Msc structures and their components, some of the design considerations for Msc structures, why we might want to consider using alternate backfills, and then look at ESCS as Msc type backfill, what effects that may have, and then look at a couple of other alternate backfills that Jack didn't mention. And then I think Jack is going to have a Q&A at the end of his presentation, so we'll kind of omit that out of mine. So let's get started by taking a look at what mechanically stabilized earth systems are. If you're in the DOT arena and you mentioned MSE walls, they're typically these walls. Let me get my pointer. It'll typically be a concrete panel wall, as you see in the upper left here. However, all of these structures are really considered to be mechanically stabilized earth systems. The one on the right here is a segmental block system, often referred to as SRW wall. Sometimes people call it a keystone wall. But anyway, they're dry stack blocks. Typically 8 inches high and 18 inches long is the standard size. There are a number of different sizes depending on the manufacturer. You have some type of soil reinforcement, either geosynthetic, mainly geosynthetic, but it could be something other than that. And then you go to temporary walls. You see this a lot in highway construction, where they have temporary grade separation where they're trying to raise one side of the road and maintain traffic on the other. These are typically a wire form wall. They got welded wire forms that form the face, and of course the soil reinforcement behind it. And then the face is wrapped with some type of geosynthetic. And then you have reinforced slopes. What I've shown here is a steep reinforced slope where they've used the welded wire forms. You can also, depending on the slope face angle, you might eliminate the need for these welded wire forms, and we'll get into that in a little bit. And then permanent wire can either be vertical or a slope. Normally those are filled with stone, and typically the wire forms are galvanized since they're an integral part of the system. So those are different types of mechanically stabilized earth systems that are in the marketplace. So let's start with reinforced slopes. Why would we want to reinforce a slope? Well, normally slopes that have a face angle of 2 to 1 or flatter are stable by themselves. They don't need any kind of soil reinforcement to be stable. Now, this can vary depending on your foundation conditions or the loading at the top, but in general, a 2 to 1 slope is pretty much stable by itself. If you want to create additional usable land, either at the bottom or at the top, you can steepen up the slope by adding some soil reinforcement to stabilize the slope. Excuse me. Let's look at the nomenclature or the components that make up a graded Msc slope. First, you have your foundation materials, and that's typically determined by your geotechnical engineer. You have retained fill, and then you have the reinforced backfill, which is in the reinforced zone. You'll have primary reinforcement, which is normally a uniaxial type geosynthetic material. Normally, these are placed no more than 4 feet vertically apart. The length of these, general rule of thumb is about 1 times the height. So if you got a 10-foot high slope, you'd have a 10-foot long primary reinforcement. Now, again, this can vary depending on your foundation materials or your loading at the top, but a general rule of thumb about 1 to 1. And then we add secondary reinforcement, which are lighter weight, lower strength materials at the face to control superficial stability. These are normally about 4 feet in length and placed about 1 foot vertically apart up the slope, just to control superficial stability of the slope between your primary grid layers. And then, of course, you can put an erosion blanket on the face and vegetate. And this is one of the least expensive types of MSC structures that you can construct. So let's look at MSC wall components. The nomenclature is essentially the same. You have your foundation, your retained fill, your reinforced backfill. The main difference is the slope face angle. The slope face angle can vary somewhat, but typically it's considered a wall if this face angle is greater than 70 degrees. Okay, if it's less than 70, it's considered a slope. The geogrid lengths or the reinforcement lengths are somewhat less. Minimum lengths are 7/10 times the height, so a little bit shorter than a slope. And again, they can vary depending on your soil properties of your foundation and your fill materials. So let's look at design requirements. What's required for the design of a reinforced slope? First, you have to be concerned with internal stability. Do you have enough tensile capacity in these geosynthetic components to make the slope stable? That's called internal stability. Then you have compound stability, which involves, it includes the geogrids or the reinforcing, but it also includes the material behind it as well. So you have to make sure you have adequate compound stability. And then there's global stability, or what we call deep-seated stability, which evaluates failure surfaces falling behind the soil reinforcement. And then, of course, direct sliding of the reinforced mass. Okay, so for walls, there are two mechanisms that you have to be concerned with. It's internal stability. And for that, you have to be concerned with the geosynthetic strength. It could be a geosynthetic, it could be steel, depending on the system. You have to be concerned with pull-out capacity of your soil reinforcement. And then connection strength of the reinforcement to the facing materials. The other mechanism would be external stability. And by that, we refer to sliding of the reinforced structure, overturning of the structure, bearing capacity, and of course, global stability. So let's take a quick look at some typical design soil properties that we see for the materials in an MSC structure. You'll notice we go from fine-grained materials, which have a fairly low strength, to, say, a crushed stone, which has a much higher strength. These materials at the top would typically be a retained or a foundation soil. The ones at the bottom you would see mainly in the reinforced zone, which would be, well-graded sands up to a crushed stone. And you notice the strength of these materials is much higher. Unit weights are generally about the same in the 110 to 125 range. Those are moist unit weights. Okay, so how do these soil properties affect the MSC structure with regard to reinforced fill? Well, a change in friction angle of only 2 degrees of your reinforced backfill can increase or decrease the load by about 10%. So this can be very significant in determining what type of soil reinforcement you need, what the length may be in the MSC structure. Similarly, unit weights, a change in 10 pounds per cubic foot in the unit weight can also affect the load by about 10%. But the presence of water can affect it by as much as 50%. That's why it is very, very important to keep water out of the reinforced zone. Most all failures of MSC type structures are generally the result of water, groundwater that it's not designed for, or inundated structures where you have a rapid drawdown type condition. So drainage is of utmost importance in the design of an MSC structure. So let's look at reinforced fill gradations. The requirements are going to vary depending on the design method that you use. Most DOTs are going to require an AASHTO design methodology. You'll notice here that the fine content, or the amount of fine materials less than 200 CIV, or 0 to 15%. The MCMA is used more for private commercial type work, and you'll notice the fine content there can go from 0 to 35%. Slopes can go up to 50% of fines, and that's why those sometimes are the least expensive grade separation system that you can use. So let's switch gears now and look at soil reinforcement considerations. FHWA has put forth these recommended values for electrochemical properties. You have to be concerned with erosion or degradation of steel reinforcement in structures. You have resistivity values, pH 5 to 10, chloride, sulfates, and organic contents. However, if you use geosynthetic reinforcements, about the only concern you have is pH values. You don't have to worry about erosion or degradation of these materials due to electrochemical properties. Okay, so let's switch gears again. Let's take a look at condition of America's infrastructure. Every 4 years, ASCE evaluates the infrastructure of the United States. They just completed this study this year in 2001 or 21, and the overall grade is a C-. Now you look at that and you say, well, gosh, that's not very good, but it's actually up from a D+, which was 4 years ago. These are the various items that they look at: aviation, bridges, dams, etc. In this report card, the values you notice range from a B in rail to a D- for transit. Most all of these are C's and D's, with no A's anywhere. So what do these grades mean? Well, a grade of C indicates that it shows signs of deterioration. It requires attention. They got significant deficiencies in condition, functionality, and increased risk. Grades of D means they're mostly below standard. They're approaching the end of their service life, and there's a strong risk of failure. So that doesn't give you a real warm, fuzzy feeling the next time you're on a high-speed train somewhere when you have rated as a D-. Okay, so ASCE also evaluates the funding estimate to bring our infrastructure back up to acceptable levels. You can see this table is from 2020 to 2029, and these values are in billions. So this is $5.9 trillion in order to get our infrastructure back where it needs to be. Before the infrastructure bill, it was currently funded at about 3.3, which leaves us a funding gap of about $2.6 trillion. So essentially what we're doing is paying about half of the infrastructure bill to get our systems back up to where they need to be. Now, the infrastructure bill will help that somewhat, but we're still not going to get to the $2.6 trillion deficit that we need to get everything back up to where it needs to be. So with this, what can we do? Well, you either have to increase funding or you have to decrease your construction costs. And one way of doing that is to look at alternate types of backfill materials. In terms of aggregates, the U.S. doesn't have an endless supply of affordable quality aggregates. USGS did a report years ago, and they estimated that it would take about a 70% increase in the aggregate production just to get our infrastructure back where it belongs. Now, 70%, that's huge. Some of the aggregate development is prohibited by encroachment. And by encroachment, I mean building of subdivisions or cities expanding their city limits in areas where backfill materials are obtained. Some aggregates don't meet the quality requirements, such as the electrochemical requirements that are put forth. Also, aggregate is pretty widespread, but it doesn't occur everywhere in the United States. This is a map, again, by the USGS that indicates areas of the country where you have limited occurrence of aggregates. And you notice these are along the Gulf Coast, up the Atlantic coast, and pretty much in the upper Midwest area. So what does this mean? Well, haul distances obviously increase the cost of your backfill materials. It's estimated that haul distances of 30 to 50 miles can double the cost of aggregates. And I can attest to this because where I live right here in southern Alabama on the coast, our stone price is about $40 a ton delivered. And that's mainly because we don't have locally available stone in this area. We have to either barge it in or truck it in from a long way away. If you go to the central part of the state, just outside of this zone that they've indicated here, stone is much more plentiful, and it's about $15 a ton. So it's a huge difference just due to transportation costs. So, ESCS materials, as Jack mentioned, these materials are becoming more and more available and used more and more. As he talked about, they use raw materials. They heat it to high temperatures to expand it. And then when it cools, it traps these gas bubbles and makes it a very lightweight aggregate. It's crushed into various gradations, and it creates a very lightweight construction material, which, as Jack mentioned, is about half of what a quarried aggregate would be. Availability of ESCS. Jack showed this illustration earlier about locations. And by coincidence, the locations where this material is available pretty much agrees with the areas where aggregate is limited locally. So, it's definitely, ESCS will be a definite option for you if you happen to be in some of these areas. Okay, so ESCS as an MSC backfill material. Advantages, it's got a very high shear strength. It's lightweight, which can accomplish or overcome some of your foundation problems if you have those. And it also meets electrochemical properties. If you recall this slide from earlier that showed the properties, the shear strengths and the unit weights of typical aggregate materials, the ESCS, again, is higher in shear strength generally, and about half the unit weight. And if you recall this slide from earlier, a change in friction angle of 2 degrees decreases or increases the load by 10%. Unit weight, similarly, 10 PCF will increase it or decrease the load by 10%, which can increase or decrease your soil reinforcement requirements behind the wall. So why is this important? Let's take a look at maybe a typical application. This could be, say, a bridge abutment. This is a conceptual section, say 500 feet in length. It's not uncommon. 20-foot high wall, 50 feet in width, founded on some sands, which are underlain by soft soils. And let's assume for this illustration that these soft soils are such that the settlement and barrier capacity won't support the structure above it. So you have to include some rigid inclusions in order to prevent problems with bearing and settlement. Normally, when they have rigid inclusions, they'll construct a load transfer platform above that. So let's put some numbers to this and just see where we might end up. The wall materials themselves, 20,000 square feet, $15 a square foot is kind of a general middle of the road price. Sometimes it's more, sometimes it's less. It's about $300,000. Your MSC backfill, let's say it's about $15 a cubic yard. Again, that's pretty much, middle of the road cost. And then the cost for the rigid inclusions in the LTP can be as much as over $1 million. So the total cost of this would be about $1.6 million. Well, the value proposition of using a lightweight backfill material in this reinforced zone is that you can eliminate the load transfer platform and the rigid inclusions. The change in this lightweight, let's assume that it would eliminate your bearing capacity and settlement issues. So why is this important, or how does this the numbers work out? Well, as you mentioned earlier, the unit weight and shear strength of this material can decrease the lateral load of the soil reinforcement requirement. So the wall backfill materials goes to $12 a square foot from $15 that we had earlier. The backfill material cost, the ESCS, can be much higher. Let's assume, for instance, in this example, is $60 a cubic yard versus $15 for a normal aggregate. But the big advantage is that you can eliminate the highest cost item, which is the rigid inclusions. By doing this, you come up with about 1.35 million versus about 1.6. So it gives you a savings of about $250,000, 16.5%. So that can be a huge advantage for using the ESCS as a lightweight backfill material. Some other examples of, alternate backfill materials that you might use would be some recycled backfills. Recycled concrete aggregate, or RCA, is being used more and more often, and we'll have an example of this in just a minute. Reclaimed asphalt, or RAP, we use this quite a bit in highway construction, not so much in Msc wall construction, but it is being looked at, and we'll take a look at that in just a minute. And then, of course, coal combustion products, fly ash. All right, so recycled concrete aggregate, shear strength is pretty much the same or very similar to what a conventional backfill material would be. This is a crushed aggregate about 55 degrees, the crushed concrete about 54, so essentially the same strength. And to give you an example, this is a project that Tensar was involved in New York, Major Deegan Expressway. About 200,000 square feet of wall face area. It required 100,000 cubic yards of reinforced backfill. Now, this particular contractor had another job, another large job, where they had to demo a lot of concrete. So they were able to recycle that concrete from another job. They got it approved as a backfill for the MSC wall. Now, the advantage of that was a savings of about $4 million. So, as you can see, that's a huge advantage in some applications. However, With the RCA, there are some drawbacks. You'll notice this picture here is kind of hard to make out, but this is calcium carbonate that has blocked a drainage pipe. You know, the fines in the crushed aggregate, concrete aggregate, and water can form calcium carbonate. So the current recommendations, if you use a recycled concrete, is to not use it where it's expected to be inundated, such as coastal areas where it's affected by tidal fluctuations. Limit the amount of fines to about 10%, and include drainage provisions to prevent water infiltration into that zone. So that's recycled concrete aggregate. Reclaimed asphalt pavement, or RAP, has been used in highway construction quite often. You can see here, these are the percent of RAP in these various states. These, now, granted, these numbers are a little old, but they're probably still very similar. You know, they'll mill up the old asphalt and reuse it in the new asphalt. It has not been used a lot in MSC structures, but it is being considered. And there's currently a study going on by the University of Wisconsin at Madison. It's a two-phase study. The first phase is completed. They looked at geotechnical parameters of an RAP. And the second phase, which hadn't been done yet, is to construct a full-scale test and instrument it to see what the effects of using RAP as MSC backfill might be. The results from the phase 1 test, you got very high shear strength, 42.6 degrees for peak strength, but they're concerned about long-term creep effects by using RAP, so they suggested reducing the peak strength by 70%, which gets you down to about 29 degrees, which is kind of on the low end of what you would want to design an MSC structure for. So it remains to be seen where this is going to be a viable option or not. Another option, coal combustion products. These are produced by coal-fired power plants. They're basically the flue gas scrubber sludge, or the FGD, is combined with fly ash and lime to stabilize it. It's produced in a number of locations in the U.S., and it's used mainly in highway construction, but it also can be used as an Msc wall backfill. This is an example of a project that we were involved in years ago. It's the Cane Run facility in Louisville, Kentucky. It's a plant owned by Louisville Gas and Electric. Due to the less expensive natural gas, they decided to decommission the site, and they wanted to increase the capacity of their landfill. And by doing this, they constructed an MSC wall. This is that structure that we showed earlier with the wire forms and a very steep face. The maximum height was about 72 feet, and there was about 45,000 square feet of area. This was completed in 2014. Another site, similar, in Kentucky. It's owned by Big Rivers Electric Corporation, and they wanted to increase the capacity of their existing landfill. And they used coal combustion product as the backfill in this structure. This was constructed in 2018. You can see the maximum height is about 40 feet, and they use the coal combustion products for that. Now, reinforcement considerations. You know, we looked at this earlier about the electrochemical properties, and I mentioned, you know, pH is a major concern for soil reinforcement. 5 to 10 if you're using steel, 3 to 9 for polyester, and polypropylene and HDPE anything over 3. So typical pH values of recycled concrete is greater than 11. Coal combustion products can be up to 13. So that essentially eliminates steel as a soil reinforcement option. and essentially eliminates polyesters. So you're left with polypropylene and HDPE for these types of applications. So that's a very important consideration when you're designing structures using these types of backfills. Okay. So lightweight fill considerations, you know, their cost, availability, and environmental savings can certainly make the use of those important. Engineering considerations, as I mentioned, the lightweight fill material can sometimes overcome settlement and bearing capacity issues. And then, of course, design considerations. You know, the lightweight, the higher strength can affect your soil reinforcement and decrease the cost of your overall structure. So with this, I'm going to turn it back over to Jack to finish the presentation. You got it, Jack?
I do. Thank you, David. Sorry, I had to do a couple of clicks there.
No problem.
Appreciate the very informative discussion about the impact of using lightweight fill materials on MSC structures and the potential to you know, eliminate perhaps riskier ground and other riskier ground improvement techniques when lightweight fill materials are used. That pretty much concludes our session for the day. And if there are any questions, you know, feel free to unmute yourself and ask them, or type them in the chat box. And we'll try to take a couple here. We're bumping up against the top of the hour. So, but if there are any questions, please either ask or type them now.
Could I ask questions?
Yes, you can.
On a concrete retaining wall, you know, typically with the heel, you're using your unit weight of your backfill material as stability for the lateral load against the wall. Which does the as a potential backfill to a regular conventional concrete retaining wall, like you get these standard details are already worked up. How does using the lightweight aggregate affect the factor of safety overturning? Do you pick up, but you reduce the lateral pressure enough to negate the effects of the lighter backfill material that would increase the heavier the material would give you more overturning resistance?
You want me to answer that, Jack, or you got it?
No, please jump in.
Well, you know, as I mentioned in the presentation, the lighter weight backfill reduces the lateral pressure on the wall. So, you know, it should reduce your overturning issues, and possibly reduce the heel of, say, a reinforced type wall.
I'm just saying, if you didn't reduce the heel, if you know, I guess that, you know, yes, you got lighter loads, but then you also have less resistive moment to the wall because of the lighter weight. So does your at the rate of your losing resistance due to the lack of dead load on the heel, is that counterbalanced faster by reduced lateral load or pressure?
Yeah, you know, it's something you'd have to look at in design, but my guess is it would probably offset. You know, it would reduce your overturning issues and also reduce your sliding issues. So with the same width of heel, it's probably going to be a trade-off versus a heavy backfill versus a light backfill.
Right. Okay.
Okay, thanks for the question. We've got one in the chat box talking about, are you aware of any lightweight aggregate materials used in geotechnical road applications with an absorption rate below 2%? Apparently, this person has a DOT application or DOT spec asking for a lightweight material with a maximum absorption rate of less than 2%. Not aware of a rotary kiln produced lightweight aggregate that has an absorption of less than 2%. But there might be some other lightweight aggregate options that would meet that criteria.
Yeah, I'm not familiar with some of the others, other than ESCS. I'm not familiar with the absorption rates on those, so I really can't answer that question, I don't guess.
Yeah.
Hi, this is Suprita Reddy. I have a question about like low strength soils, and then in order to reduce the settlement using lightweight materials on top. I'm sorry I missed the first part of this presentation because of other meeting that I needed to attend. So if I missed it, I'm sorry for that, but just wanted to get a view on it. So the use of lightweight material will reduce the settlement of soft material, but at the same time, how would it be placed and compaction issues? Like, let's say I have soft material and I'm placing this lightweight, how would it compact on soft material? Am I being clear? Or the placement issues, like the actual construction issue, will there be any issue?
Well, if I understand you correctly, I don't think you should have fewer issues if the bridge lift material you're pushing over a softer soil is a lighter weight material. But just like with any of those situations, the critical thickness there is what's important. Is how much thickness do you need to not overstress your soft soil underneath? And certainly a geogrid under the material in that application would be an ideal solution.
I see. Thank you.
Sure. All right. I don't see any other questions in the chat box. So I think since we're past noon, we'll try to wrap it up. The email addresses for both David and me are on this slide. So if you have further questions that you think of, or want some clarification in some of the material that was presented, please drop us an email. For additional information on ESCSI, you can find that at escsi.org. And for additional information about Tensar Corporation, go to tensarcorp.com. So I want to thank David for a great presentation. Appreciate you being a co-presenter today. Thanks to all the attendees that hung in there for a little over an hour. Really appreciate you participating, and appreciate the questions at the end of the presentation. We'll be sending out a survey following this, and we'd greatly appreciate your feedback. Constructive criticism is always welcome. For those that requested them, PDH certificates will be sent out a little bit later. So hopefully, again, hopefully this presentation was informative. We hope you'll join us for other, ESCSI focused webinars, and for a list of those, they're posted on the ESCSI.org website. So thank you all again very much. I hope you have a great rest of the day, and Merry Christmas and Happy Holidays.